Good afternoon. Welcome to course Thermodynamics of Materials. Today we are into the lectures 105 and 106. Today we will be discussing, we continue with solution thermodynamics, and we have completed this part last class. Integration of the Gibbs equation for a binary system. Last day we have completed this. So today we will take up a new topic, namely regular solution. So, but before I start, I should say this. Okay, before I start, I should make one correction, very serious correction. Very serious correction here. Small though, please follow last class. Gamma B0. Please see here, gamma B0. This gamma B0, I have by mistake I wrote Henryan activity coefficient, but this is not Henryan activity coefficient. Okay, this is actually Raoulsian activity coefficient. So I am correcting this. This is Raoulsian. Please note this Raoulsian activity coefficient. This is actually about this. This gamma B0 has something to do with Henry's law, but that doesn't mean it is Henryan activity coefficient. Okay, this is actually the slope of the activity composition curve in the dilute region, and which is given by Henry's, but the activity coefficient is Raoulsian. Okay, that is this is Raoulsian because this is actually uh, uh, is activity. This shows deviation from the ideal solution equation, Raoulsian equation, which is activity is mole fraction. This shows the deviation, and this is quantified by gamma B0. So Raoulsian activity coefficient. In passing, so let me note this. So this is all over last class, all over. So today I will start new topic, and I'll before I start. So before I start, let me specify this mistake here. One one small yet serious error in the last class. This part is which is the gamma B0 0 Raoulsian activity coefficient. Raoulsian activity coefficient. not what I wrote there, also not Henrian activities, not Henrian activity coefficient. Please note this. Please note and correct this. This is a serious mistake because later on we will see Henrian activity coefficient, the symbol for the Henrian activity coefficient is F5, not gamma. Okay, so this correction, small correction, though by mistake, okay, I wrote this. Okay, this is actually kind of slip of pen. So, but anyway, this is made up, and this is noted, and we have. So with this, let me remove last day's class all over. These are all over. So today's topic will be regular solution, quadratic solution model. This I'll take up. So let me remove this part also. So solution thermodynamics, we are still with this. Today's topic is regular solution. No, sorry. Quadratic. Wait a bit. Quadratic solution model. Regular solution. Solution. We are actually will consider typically binary system. Binary system. So this is our topic today. So I tell you one thing, that we will be interested to find the activity coefficient of any component in a binary solution or ternary solution or quaternary solution. If we know the activity coefficient in a convenient way, then we can find the activity because I'm sorry, if we know the activity coefficient conveniently at a given composition, then we can find easily the activity, which is nothing but activity coefficient times the mole fraction of the component. And once we know the activity, this activity will finally be useful in the chemical equilibrium systems. And you can consider reaction equilibrium, all chemical reactions involving solutions, alloys, that is impure phases, or in phase equilibrium, phase diagram, for example. There we can use these activities. So before, alternatively, we can find measure activity, but maybe we will have, with the help of this model, if we determine some solution parameter experimentally, we can have actually any system we can apply this solution parameters and find out the activity coefficient at a given composition and find the activity. Alternative is directly determine the activity from the compound, which may not be very easy. Okay, there are many methods. There are activity vapor pressure technique or chemical equilibrium technique. There are many methods, but they may not be so easy. Okay, may be difficult, but that is also an option. So we are actually trying to find activity coefficient as a function of composition with the help of the model. But even with this model, it is not all theoretical. Some experimental, okay, experimental, okay, is there. Experimental part is there where we will find out some solution parameters. But once they are found, they are forever there and can be applied to any systems where they are relevant. This I will explain. So for the time, let us write this. Solution models aim at aim at proposing a relation between the activity coefficient which is gamma I symbol, and composition. The symbol is xi, as well as relation between this and composition, as well as temperature. That means relation between activity coefficient and composition as well as temperature. Composition as well as temperature, gamma I, will be expressed in terms of composition, mole fraction, and temperature. Temperature say T. And temperature, ignoring the effect of pressure, which is small for condensed phases. This allows one to find the and the activity coefficient, and hence the activity, and hence the activity, which is AI symbol, which hence the activity, is the activity of a component of a component at a given composition and temperature. And temperature. Given that the still there is actually a restriction or a qualifier. Okay. Given that the solution parameters such as solution parameters such as alpha or omega or interaction coefficients, they call it I, E, I, J. This is called self interaction coefficient. This is called ternary interaction coefficients. This we will discuss later. Okay, EIG, etc. EIG, etc. are known, either are known or experimentally found beforehand, or experimentally found beforehand. So, we will find the activity coefficient and hence the activity. So, this what we will do with this activity? This is finally activity is important. In thermodynamics, finally activity is important, which we will use in chemical equilibrium or say reaction equilibrium or phase equilibrium. So, but this activity we will know from activity coefficient if we have actually some suitable model, and with the help of some with the help of some parameters, solution parameters we call it, then we can find the activity coefficient from which we will get activity. But finding these solution parameters will be actually a challenge to us. Unless we know this, we cannot use the relation between gamma and composition. So we must use this, we must know this beforehand. Or if we don't have, then we have to find out ourselves experimentally. Ourselves, okay, beforehand. Okay, the values of activities, the values, so let us have a paragraph then. The values of activities thus found, and this I can write preamble. This you can write, this is the preamble I am giving you, preamble to this solution model, why it is important, what we will do, what are the challenges. Okay, the values of activities, thus found will be utilized in chemical equilibrium. In the chemical equilibrium, chemical equilibrium, for example, in the chemical equilibrium, such as reaction equilibrium or and and phase equilibrium and phase equilibrium calculations. This came in the chemical equilibrium calculations. This is thus finding the activity coefficient of a component of a component of a component at a given composition and temperature of the solution, temperature and of the solution is one of the biggest challenges biggest challenges in the study of in the study of solution thermodynamics. That's this is the preamble. So preamble is over. Preamble is over. Now we take up actually the model, regular solution model. So let us start this. So next is start regular solution. I've already given the caption regular solution model. So Margules is better. I start from the top. I think these are all over. Start from the top. Start. Start. Margules Margules 1895 suggested a power series. For the composition dependence of the activity coefficients of the activity coefficient gamma A and gamma B of a binary solution AB, of a binary solution AB. AB. What is proposed? AB. ln gamma A is alpha 0 plus alpha 1 XA plus half alpha 2 XA square plus 1/3 alpha 3 XA cube, and this is an infinite series. This goes to infinite. Likewise, ln gamma B is what? Beta 0 beta 1 XP plus half beta 2 XP square plus 1/3 beta 3 XB cube. Now, in the first place, in the first place, we consider that in the first place we consider that we consider what? We consider that the above relation is valid for the entire composition range of the solution. Entire composition range of binary means xb is 0 to xb is 1, or xa is 1 to xa is 0. Entire composition. So in the first place we consider that the above two relations above two, no, sorry, in the first place I am very sorry. Okay. Acha, note here, sorry, one thing note here, alphas and betas are function of temperature, Note that. Then it will be gamma will be function of temperature and composition, as it should be. Okay, so effect of pressure we have ignored already. I mentioned in the first place we consider that the above two relations extended to infinity are well represented are well represented by the terms up to the quadratic ones only. So we consider that the above. That means we will ignore this cube, xa cube, xa4, etc., or xb cube, xb4, higher power beyond square, quadratic, we will not consider. We consider that this up to quadratic terms the relation up to quadratic terms will be good enough to represent the activity coefficient composition relationship. So this according on only. So this is, if we do this only, that is what, if you consider this, then you can write, give a name to this equation. Equation name is 1, 2, 2. That is ln gamma A is what? Alpha 0 plus alpha 1 xa plus half alpha 2 x square. Okay, and ln gamma B is what? Beta 0 plus beta 1 xb plus half beta 2 xb square. Okay, actually I said something different. That I said, actually initially I am considering that this relation is valid over the entire composition range of the system AB, means from xa is 0 to xa is 1, or xb is 1 to xb is 0. This I'll take up next. Now I'll take up. First is what? We'll just curtail this expression, long expression, curtail by up to this term. Curtail the terms beyond these terms. So make it shorter and make it limited to quadratic. Hence the name quadratic solution model. So quadratic we consider. Up to quadratic we consider. Other terms will be curtailed off. So this now next one in the first. Next we consider, another consideration is there. Next we consider, what we consider? Next we consider that the two relations, I give a name to this, equation 3, equation 4. Next we consider the two relations, the two equations, that the two relations equation 3 and equation 4. Equation 3 and 4 are obeyed over the entire composition. Entire composition range of the solution. That is, xb is 0. What is this? Oh, comma. Xb is 0 to xb is 1. Like say, you can see here, I can show you this. What is the meaning of this? This is your activity composition diagram. Suppose this is your Raoult's law. Okay, this is actually activity versus composition, and if you gamma is activity V by xp, so you can plot gamma B versus xb. Again here xb is 0, xb is 1. And this is A, this is B. Here A, B. Xb is 0, xb is 1. Suppose this says, this relation quadratic relation say like this. Suppose this is the relation. This is obeyed over the entire range. Xb is 0 to xb is 1. Or conversely, xa1 is 0 to xa1 is xa is 1 to xa is 0. So this is valid. But later on we'll see in this regular model we consider this. Later on, in a modified regular solution model, we will see that this is not possible. This is very difficult. It is a tall order that this relation will describe the entire composition, will address the entire composition or describe the activity coefficient composition relation for the entire composition region, whole region. It is too much maybe. Okay? It may not be always feasible. So in that case, we will modify this subsequently, and we will take up that on the modified regular solution model. There we will consider it maybe up to here, up to this zone, this will be valid. This modification will be valid, and likewise this. Okay, so this is this side also. This will be valid modified. So three zone. Okay, three zone model, that may be. So, but here where will be sufficient. Here we consider that this, if you are interested in this part, this will valid up to certain composition, but this is modified. This is modified, but not currently. Currently, we consider this gamma b xp relation is for the entire composition. If this happens, then what will happen? If this happens, then what will write? And this side actually, this modified, I tell you, this side is B is solute concentration up to this point. Maybe the relation, modified relation will be valid. And this side of who is solute? A is solute. And then A's equation, A also similarly has equation. This is Raoult's law. Have some this equation. This is also valid up to certain composition like this. This is not currently considered. This will also, in fact, we are interested in solute side. B as the solute and A as the solvent. We'll consider this subsequently. But for the time being, very simple consideration that it is valid over the entire composition. So XB is 1. Okay, very good. Which gives alpha 0 is 0, beta 0 is 0. You can very easily find out why. How will you find this? So when XB is 0, how you write this? Alpha 0 is 0, beta is 0. Noting when XA is 0, consider entire range. XA is 0, then what is the XA is 0, then what is the value of gamma A? XA is 0 means that is when X is 0, we have what we have? Tell me. X is 0, XB is 1, and XB is 1 means pure. When XB is 1, we know gamma is, it's actually activity is 1, XB is 1, gamma is activity over XB means 1 over 1 is 1, gamma B is 1. So we have XB is 1 and gamma B is 1. And if gamma B is 1, what is ln XA is 0? Okay. And XA is 0. What is XB is 1? Gamma B is 1. And ln gamma B is what? 0. Achha, I made a mistake, serious mistake. A serious mistake. Please, here, right from here. I write from here. Sorry. Please change this. Please change this. This is gamma A in terms of xp square, xpq, and gamma B likewise in terms of. I'm very sorry. XA. This is also XA cube. So here also similarly, this will be xp gamma A. This will be xb square, and this will be Xa, this will be Xa square. And next, now you take up this. So when this is valid for the entire composition, then you write this when Xa is 0, is Xa is 0, X square is 0, then we have what? When X is 0 means Xb is 1, and then gamma b is 1, and ln gamma b is 0. So what you get from this? This is 0, 0, X is 0, 0, 0, 0 means beta is 0. Beta 0 is 0. And similarly when, similarly, write this. Achha, can I remove this part? Can I remove this part? Similarly, tell me what? Similarly, tell me when xb is 0, when xb is 0, that is xa is 1, and when xa is 1, we know gamma a is 1. Pure substance, gamma a is 1. Activity is 1. Gamma is 1. So you substitute this ln gamma a. What is ln gamma a? Is 0. So 0, xb is 0, 0, 0. What you get? Alpha 0 is 0. So these are the two things that we get from this consideration. Second consideration, three considerations coming. First, this that it is up to quadratic, not beyond, not higher powers anymore, or any higher powers like cube 4, no, x4, x5, no. Second consideration is what? These relation is valid over the entire composition. It describes this gamma b versus xb described by this equation and valid for the entire composition. So this immediately gives us alpha 0 is beta 0. Substitute this, then as a result of which alpha 0, applying the two equations, then reduce to these two equations. Reduce to what? Write once more. Ln gamma a is alpha 0 is out, alpha 1 xp plus half, oh sorry, half alpha 2 xb square. Okay, and ln gamma b is what? Beta 1 xa, beta 1 xa plus half beta 2 xa square. Clear? Call this 5 and 6 equation number 5 and 6. Okay. Now applying the pertinent application of Gibbs 2m equation. Applying the pertinent Gibbs 2m equation, what is the pertinent? Xa dln gamma a plus xb dln gamma b is 0. If we apply this Gibbs 2m equation, we have what? Well, let us try this. We have what? Try this with this xa dln gamma, dln gamma on the first one, on equation 5. Alpha 1, you check this, I am doing alpha 1 dxb. I am moving on. plus what is this d of this 2 alpha 2 xp dxp. See, no problem. Xa dln gamma a is what? Plus xb dln gamma b is 0 means minus xb dln gamma b. So minus xb dln gamma b. Do this differentiation beta 1 dxa plus beta 2 xa dxa. Now noting two things. Noting xa plus xb is 1, rather xb is 1 minus xa in the binary, and what? dxb is minus dxa. This we have what? We have see dxb. See one thing you see dxb dxa minus dxa minus. So cancel out. Cancel out. Okay, dxb. Okay, is what? dxb minus dxa. You have this, and then you write this and express b in terms of a. So you want to write the terms, mole fraction terms, all in terms of xa or x square, etc. No xb. So we want to bring it into a common terms like xa or x square in terms of xa. Then we will equate the coefficient. Helps us equate the coefficient. So start. So xa alpha 1. So alpha 1, I'm writing this way, alpha 1 xa first term plus what it is, plus alpha 2 xa xb. What it is, xa times xb means 1 minus xa. So left hand side is okay. Right hand side is what? Beta 1 plus, oh, I'm sorry, there is some xb here. So xb here means 1 minus xa times beta 1 plus beta 2 xa. Okay, beta 1 plus beta 2 perfect. So all x's, no xp anymore. Okay, so only I am giving a star here. Go. I think this is no more required. So what do we have? Star or just again alpha 1 xa and alpha 2 xa. So alpha 1 plus alpha 2 xa, alpha 2 xa, then minus alpha 2 x square. Right hand side is what? You do this first is beta 1 alone, beta 1 plus beta 2 xa minus beta 1 xa. So plus beta 2 minus beta 1 xa. Okay. The last term is minus beta 2 x square. Now this side is constant xa x square. This side no constant but xa x square. Now we can compare coefficient very easily. This coefficient must be same. So comparing the coefficients of the constant term, xa term, and x square term between the left hand side, and the right hand side. between the left hand side and right hand side. Expressions you write. You compare. So constant term, one by one. Constant term is what? You have the constant term here, beta 1, and there is no constant term. So that means beta 1 is 0. Next is XA term. XA. XA term, what you have? Left hand side, alpha 1 plus alpha 2 is what? On the right hand side, beta 2 minus beta 1. And we can immediately simplify it to beta 1 is 0, so is beta 2. Next is X square. What you have? X square. Left hand side is alpha 2 minus alpha 2, and right hand side is minus beta 2. So alpha 2 is beta 2. Okay, alpha 2 is beta 2. Now this leads to what? See, alpha 1 plus alpha 2, this line is beta 2. Or here we get alpha 2 is beta 2. This alpha 2 is beta 2. So this beta 2 cancel, leading to alpha 1 is 0. So what we get? What we get out of this? So finally is what? Alpha 1 is 0, beta 1, well, wait a bit, beta 1 is 0, and alpha 2 is beta 2. These are the conclusions. Applying, after we have applied, that gives you an equation. Okay, so put it back into the latest equation is what? 5 and 6. Put it back here. So, so this. So equations. So equations. What are they? 5 and 6. Further reduce. Further reduce to let me remove this. Further reduce to what? Tell me. Here ln gamma A 5 and 6. Ln, write nicely. Ln gamma A is what? Alpha 1 is 0, out. Alpha 1 is 0. Half alpha 2 xb square, and ln gamma b is what? Again beta 1 is 0, out. Beta 1 is 0. So half beta 2, again half beta 2 is again alpha 2. So write, express in terms of alpha also. Any one of them, that will be helpful. X square. So this is, you may call further simplify as alpha xb square. Okay. Actually not here, I am writing separately. Actually, letting half alpha 2 is alpha. Alpha is a parameter, but we have actually a more formal parameter later on coming, but alpha is actually a kind related to solution parameter, but alpha. So alpha is what? Half alpha to alpha, then we have got what? Ln gamma A. So half alpha to alpha xb square ln gamma b. Sorry. ln gamma b is ln gamma b is what? Alpha x square. This is the final form of the regular solution. Okay, this is what we should note. So the give equation name is what? What is the name? What we have? 5, 6. This is 7, 7, and this is 8. Note, alpha is a function of temperature. Initially, I told you these alphas and betas are function of temperature. Alpha is a function of temperature. What does it mean? What does it mean? What does it mean? Alpha is a function of temperature. That means that is so gamma A and gamma B both is function of what? Is composition. XB, XB are compositions. Alpha is function of temperature, is function of temperature composition, as it should be. I already explained. Gamma B is a function of temperature composition and pressure, but pressure effect is ignored. So this is actually regular solution equations, but we will have more to do on this start from this. Okay, so I give this here, say star, double star, perhaps. Still we may utilize this space, double star. Now we'll get more into the thermodynamic relationships and thermodynamic properties we'll consider, like say now GA bar excess. Let us follow. We are studying regular solution. Regular solution is characterized by these equations. But we have so far applied two conditions, two assumptions maybe. Two so far, two. One is the relation is considered up to quadratic terms, not beyond. And second is what we have considered, the relation is valid over the entire composition. These two. There is another coming soon. That is also very important. Now let us develop that. Now GA bar excess is what? Tell me. GA bar excess, as you remember, RTLN gamma A. So is what? Alpha RT XB square. This is known as omega XB square. Call it equation 9. And similarly, GB bar excess, similarly, omega I will explain omega. GB bar excess, similarly, RT ln gamma B is alpha RT XA square omega XA square. Call this equation 10. Note, omega is alpha RT, but alpha is a function of temperature. But alpha T is not a function of temperature. What does it mean? Alpha is a function of temperature. R is not, R is a constant. That's constant. Alpha is a function of temperature, but alpha T is not function of temperature. Means what? Alpha is inversely proportional to temperature. Hence, omega is not function of temperature anymore, because alpha T is a constant. Alpha is inversely proportional to temperature. So omega is not function of temperature. That is interesting. So omega is not function of temperature. Function a constant. Temperature independent constant. This omega is, or you can write also, or alpha, just a juggle around this. Alpha is omega by RT. Since omega is a constant, R is a constant, that is alpha, sorry, alpha is inversely proportional to temperature. Alpha is a function of temperature, of course. Inversely proportional to temperature. Alpha is, note, note here, note the term omega is called the solution parameter. Is called the solution parameter. So one part is over. One part is over. We have used one thing. Third condition we have used. Third condition. What is the third condition? That considering alpha is inversely proportional to temperature. Two conditions already. Third condition, alpha is inversely proportional to temperature, which means alpha is a omega by RT is a constant by temperature. Omega is a constant, R is a constant. So inversely, this dependence of this temperature dependence of alpha we have considered in the regular solution model, which is the third consideration or third assumption. It is just inversely proportional to temperature, so that you may write here alpha T is constant also. Shall I write here? Alpha is inversely proportional to temperature, or you write alpha is a, you write here alpha is function of temperature. Now we understand what type of functionality. It is inversely, so that alpha T is omega by R is a constant. Alpha T is constant. Good, very good. This term we call a solution parameter. Let us move on. So next, hence Gxs, you know, or delta Gxs. You recall Gxs or delta Gxs, same thing. Same thing. Gxs is, I am writing Gxs is what? Xa Ga bar Xs. Recall integral partial integral Xs P energy integral molar partial Xb Gb bar Xs. Substitute the values. What is you are getting? Xa Ga bar Xs is what? RT ln gamma is omega x. Finally omega xb square plus xb what? Omega x square. Okay. Okay, very good. X square, what you get out of this? Omega x xb in common. What you are have here? Xb plus xa. What is this? Xb plus xa is what? By binary solution 1. So what is you are getting this? So or you write place Gxs is omega xa xb. Gxs is omega xp. Can you tell me, will it be a function of temperature? Very important issue. Very important issue. Is it a function of temperature? Omega is not function of temperature. Omega is not function of temperature. And Xa is a composition. It's not. So is not function of temperature. You know this. So Gxs is omega xxp Gxs. Now tell me, omega xp is not function of temperature. Hence, give a triple star. Triple star right from here. This is all over. All over. Triple star. What you get? Now once we have Gxs, how to get Sxs? Now Sxs is what? Tell me. Because any time, any day in thermodynamics, S from G, what is the derivative? Del Gxs by del T. Recall constant pressure composition. This part I discussed number of times. SXS. If it is mixing, this will be mixing. If it is zero, it will be zero. Standard state. Everything. Okay. Or delta G, delta S zero, delta G zero. But there is a negative sign because S is minus. Now, can you tell me what is this value? Tell me what is this value. I will be very happy. See here, and report here. See this expression and report here. What is SXS? This is not a function of temperature. The ddt of anything not function of temperature is, this is one great characteristics of regular solution. Okay, so I'll summarize the properties. So this is GXS is here, SXS is here. Okay, good. Oh, I'm sorry, these are not. Give me rest. Give me rest. Here is what? 0. 0. Next is what? HXS enthalpy GSH. HXS, what happens? HXS is what? Please tell me. HXS is what? GXS plus TSXS. G is H minus TS. G is H minus TS. H is G plus TS. So GXS, SXS is 0. So it is GXS. So this is GXS. Okay, happy. Okay, GXS. Or delta HXS. G means HXS means delta H. H means delta H. XS is delta GXS. Delta GXS, or what is delta HXS? Delta HM, the solution under study, which is regular solution, minus what? XS is always measured over, I'm sorry, H, delta HM over what? Ideal solution. Ideal solution. That is XS is delta GS, delta GXS. Or what is this delta HM ideal? Everyone knows what is this value? 0. Or what we get out of this? Delta HM regular solution is delta GXS regular solution. Regular solution. So this you get this. Okay, very good. And what is this? Delta GXS regular is what? Nothing but GXS. I have given there GXS is delta GXS is what? Omega XXP. You can write that omega XXP. You can write this also. Is omega XXP here from here. Okay, very good. Right here. Okay, is right there. Okay, yes, written here. So now I summarize the properties. Shall I? I summarize this. This is the final one. I will not remove this. 7, 8 I will not remove, but I will remove other ones. Okay. So for regular solution, so I am summarizing. right? 1, 2, 3, etc. Huh? Delta Hm. What is the delta Hm? Tell me. What is that? Delta G excess. And delta Hm is delta G excess. What is this delta G excess? You know what is the? Okay. So, shall I write this? Okay. Delta G excess is already there. Okay. So write this. Xa Ga bar excess. Right. A few steps you write. I mean, kind of extra lines maybe. So you say what Xa Ga bar partial, integral partial is Xa. What is Ga bar excess? Is recall this RT ln gamma A plus XP RT ln gamma B. What is this? Right. RT common Xa ln gamma A plus XB ln gamma B. Xa ln gamma A, XB ln gamma B is equal to is you write this is a moment ago you wrote this. A moment ago you wrote this. Where you wrote? Here you wrote is omega XP is omega Xa XP. Omega is the solution parameter I have written somewhere. Yes, solution parameter. Is delta Hm. What else? What is delta Gm? Gm is like any solution, regular, any real solution. General relationship. What is the delta Gm? Recall like this, RT RT. Tell me what is delta Gm? RT. This is excess is what? Gamma, and delta G excess is gamma, and this is activity. RT XLN A plus XPLN AB. And what else? What else you write? Zero, and zero is delta SX for regular. For regular, delta SX is zero. You wrote this. SXX means this delta SXX is zero. So what is this? Delta SM regular minus delta SM ideal. That is delta SM regular. I am talking about regular solution, so I am not writing regular anymore. Everything is for regular, regular, regular. So delta SM is what? Delta SM regular is zero. Zero is this is delta SM ideal. Delta SM for the regular solution, delta SM is same as the delta SM ideal. What is that value? Tell me. Delta SM ideal standard minus R XA ln XA ideal solution plus XB ln. I should slightly borrow some space here. This is very important. Will you just box this? Oh, no, no, no. It actually goes this way, this way, this way, this way. This way. Delta Hm, repeat. Delta Hm is delta G excess. Delta Hm is delta G excess. Okay. So actually delta H excess, delta Hm is delta H excess because minus delta H ideal. Excess is mix, excess is real solution minus ideal. Because ideal delta Hm is zero. So they are same. Delta H excess is delta G excess because T delta excess is zero. Anyway, delta Hm is delta G excess is what? Finally, RT XL and gamma A plus XBL and gamma B omega excess. Expression full. delta Gm as usual in all real solution are T xln oh sorry, very sorry, xln A plus xb ln ab, xln A. So this is common, very normal, and for delta Sm what it would be? Answer is delta Sm ideal. Answer is delta Sm ideal. What is that? This one. How? Quickly write. 0 is delta Xs. And what is delta Xs? You can use the property, mixing property, delta Sm regular, is real or regular, whatever you call it. Here, regular minus delta Sm ideal. And 0 is this. That means these two are same. That is delta Sm regular is delta Sm. Delta Sm regular. Since I am talking regular solution, so delta Sm means delta Sm regular is delta Sm ideal is ideal solution, minus R xa ln xa plus xp ln xp. These are the three things that we have, and in addition to what this is omega xa xb, so involving solution parameter. So sorry, omega xa xp, omega xa xp. Oh, I've written number of times omega xa xp. I've written number of times omega xa xp. So these properties are these, and this is the basic one. But here, up to this point, we have not considered the temperature dependence of alpha. We know alpha is temperature dependent. We know that alpha is a temperature dependent term. But what sort of dependence? What sort of functionality with respect to temperature alpha has? We don't know. That we have considered in the third. Third is what? Here, alpha is inversely proportional to temperature. That says, means omega is alpha t. If alpha t means alpha t is a constant, and we have called this constant is omega by r, or alpha is omega by rt, or omega is alpha t, whichever you call it. Remember that alpha is a function of temperature, but omega is not, and because alpha is inversely proportional to temperature. This consideration that alpha is inversely proportional to temperature is, if this is violated, then regular solution will be violated. Then we have to find modified one. Okay, this about this temperature dependence, okay, alpha and temperature dependence of alpha. Anyway, for the time being, consider with these three considerations, we have the regular solution set. The simplest quadratic model, maybe. Okay, so this is fine. Okay, call it equations. It is better I give some equations here. I forgotten to give the equations. That is very good. That is GAXS is what? So for regular solution, this is the one. This must be 11. Why this 11? This is 11. 11. 11. Why is 10? Why is 10? 7, 8, 9, 10 is where? 9, 10. G over X omega 9. This is 10. 9, 10. And then 11. Then this will be, give a barrier here. This is the 12. This is the 13. Oh, XA and XA. This is the 13. So with these equations, we have actually finished regular solution. Only okay, okay. Achha, let us remove this. Remove all this. We have some little bit left. And finally, I will give the summary of regular. So in fact, this is the summary, but I will give you in a more. I'll give at the end. At the end, quickly, let us start this. So let us write few lines. It may be noted. So what you have noted very clearly, delta S excess is 0. This is a characteristic of regular solution. It may be noted. It may be noted that the excess entropy, that the excess entropy S excess, which is or delta S excess. I write sometimes so that you don't confuse. For a regular solution is solution is 0. Is just 0. Is 0. This means that what delta Sm regular solution, as I told you, last one, delta Sm regular solution is delta Sm ideal. Delta Sm regular solution is delta Sm ideal solution. Some ideal solution. Thus, the entropy of mixing, entropy of mixing for a regular solution is what is same as is exactly the is considered is exactly the same as exactly the same as that of that for an ideal solution. That for an ideal solution. Ideal solution. Ideal solution. That for an what is that ideal solution? Is that when we have entropy, ideal solution means random distribution of components. Okay, random distribution of components in the solution. A and B are randomly distributed. No preference. A have no preference for A or B or B likewise. So random distribution. This we consider random distribution of components. So this is the ideal solution of the general. This is followed. This is followed from the fact that alpha is exactly inversely proportional to temperature. This gives all these things. Okay. So this gives what? See, you can see delta G excess is what? Okay, temperature independent. Delta G excess is temperature independent. Why? Because you see from this alpha RT is omega this, and once it is this delta G excess is independent of temperature. Delta X immediately becomes 0 because derivative negative and derivative, so 0. So this is the clue behind delta S excess being 0 for regular solution, or delta Sm for regular solution is same as the delta Sm for ideal solution. Same entropy change in the regular solution as in the ideal solution, namely minus R Xa ln Xa. This one, we know this. Minus R Xa ln Xa plus Xp ln Xp. So this issues from this fact, alpha is omega by RT. That is alpha is in alpha is inversely proportional to temperature. To temperature. And to temperature, proportional temperature, alpha RT being equal to omega, which is temperature independent, constant. Temperature independent constant. So I'm removing these also because I'll summarize at the end. But I have one thing on hand, so that let me finish this. Constant. Okay. So what I'm trying to do, thus let us proceed. Thus, for a regular solution, I'm trying to arrive at something. Thus, for a regular solution, what we have got, RT ln gamma A, number of times I've written, RT ln gamma A is omega xb square. Omega xb square. This is equation 9, somewhere I wrote previously, equation 9 I repeat here, equation 9, okay? Or RT ln gamma A is what? Omega is temperature independent, is constant. Xb square is a function of composition, is constant. For a constant, is a constant for a given composition. If I give a composition, say xb is 0.3, that composition given, then it is a constant whole thing. Is constant for a given composition. Or T ln gamma A, is constant as well. Okay. So or see, write this, or ln. So this is the temperature and gamma relationship, gamma temperature relationship. Or what you see, what you find here, or ln gamma A. Oh ho 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 ho. Or ln or ln gamma A at temperature T2 by ln gamma A at temperature T1 is nothing but T1 by T2. This is the T ln gamma is constant. That means if we know gamma A or gamma B at one temperature, then we can easily find out gamma at the other temperature, any other temperature, for a regular solution. So this is valid for the regular solution. This is how we will get. I want to find the temperature gamma. I have experimentally found gamma for one temperature, say 1400 degree Kelvin, 1400 degree, okay, 1400 degree Kelvin. But I want to find the gamma for same composition. Same composition. Composition is XP is zero point 0.4, XA is 0.6. 40% B, 60% A. I found gamma A, one temperature. So then, but for other temperature, I don't have to carry out experiment. So 1500 Kelvin, just T2 is 1500 and gamma A T2 will be find out because these two are known and T2 is 1500 known. So this is the property of the regular solution. Now you may be confused. You may be very much confused that you have actually one temperature dependence of gamma, but already you have started temperature dependence of gamma general for real solution. Obviously, real solution gamma, when gamma is present means it is a real solution. For real solution, you have a relationship. I will remind you of that. So which one you will use? That is for any real solution. A regular solution is a kind of real solution. So we have to reconcile this. These must follow that. That means that is the general and this is the special. Special real solution is regular solution with the three stipulations. So this is my next task, is to reconcile that previous relation with this. This is the next task. Okay. This is not lengthy though, but I will take up this. This is what, let us do this. See reconciliation. Reconciliation. Reconciliation of, recall, d ln gamma I by dt del T at pressure composition is what we call minus hi bar m partial molar enthalpy of mixing by what? Do you remember this? RT square? RT square. This was the relation. We had an integrated form that was simpler, dln gamma I dt. That I am writing. See this one, okay? With the reconciliation of this, the general for any real solution. With the what one? The regular solution. With the regular solution relation, solution relation, solution relation. What is the relation? Tell me, what is the relation? T ln gamma A is a constant or T ln gamma B is a constant. T ln gamma I, T ln gamma I is constant. We have to reconcile this. This is very useful. That is integration also. That is very simple. This is also simple. You like equilibrium constant. One temperature you know, another temperature you find. The similar situations, similar relations. Okay, reconciliation. Quickly. So start. Okay, this start. Reconciliation. D ln. This is a couple of steps only. D ln gamma I. Looks like I'll change the pen. Again. D ln gamma I by del T pressure composition. I'm writing this. Pressure composition is minus hi bar m RT square. The starting point. From this I reach there. That's the reconciliation. This you remember. Okay, go back to your earlier notes. You will get this. What is this? Please tell me. Minus hi bar m is nothing but, a moment ago we have said this is nothing but gi bar xs for regular solution. When it is true? For regular solution. Since I have to reconcile with regular solution relation, so I have to use the attribute property of regular solution. That is what this is this for regular solution. Okay, when entropy excess is zero. This is not true for other real solutions. For regular, particularly for regular solution, we know this is what. Tell me, minus gi bar excess is what? R T ln gamma a gamma I r t ln gamma I over RT square. RT square is okay. Will you cancel R? Will you cancel this t and t square? What is remaining here? Minus right tidily ln gamma I by t, or you cross multiplication, or t d ln gamma I plus side change plus ln gamma I dt, sorry, dt is 0. T dln gamma I is ln gamma I dt minus that side, when taken to the left hand side, is plus, or what is this? D T ln gamma I is 0, or integrating T ln gamma I is constant, which is actually is constant, which is regular solution, which is which is which is regular solution which is regular solution gamma I versus t relation Okay, so just at the end I'll summarize this. Okay, summarize this summarize the regular solution. This is over. So this is another important relation. You box this you will often use. I'll give you an assignment. Assignment number 9 on solution. There you will use this for regular solution behavior. Maybe possible next day we'll start discussing. So what I say? I remove this. I remove this. Just the summary. To summarize, only any non-ideal means real. Any non-ideal solution, that is real solution. Solution can behave as a regular solution, as a regular solution, as a regular solution if it meets the following following three criteria. Following three I said three, the three. One by one. One is what? One, ln gamma I versus 1 minus xi relation as given by, suggested by Margulis, as by suggested by Margulis, um, holds good for the entire composition range. Achha, I'm coming to this as second. It is Margulis is restricted. This is first. Is restricted up to quadratic terms only, not beyond. Not beyond. This is the first one. Second one, write the the ln gamma I versus 1 minus xi relation is holds good. Holds good for the entire composition range that is xi is 0 to xi is 1. Last, third, what? Alpha vector, alpha function. Alpha is inversely proportional to temperature. Third, and the last, or alpha t is constant. What is the constant name? Is omega by r. Omega being the r, omega being the solution parameter. Being the solution parameter. This leads to, remove this. This leads to the inference Si bar xs is 0, or which further leads to gi bar xs is hi bar m. That is the partial. I have written partial integral also. partial 0 means integral is also 0. That is the partial or integral molar. I am removing this. No need anymore. Molar entropy of mixing partial or molar entropy of mixing is the same as is the same as that of the ideal solution. Solution. This is the summary. This is the summary. Hello, Bappa. Bappa. Acha. Since I have some time left, actually, I still have some time. So this is all over. Regular solution over. Regular solution over. But we will consider modified regular solution when this will be violated. Which is this one? Not for the entire. This relation, this relation will not hold good for the entire composition. It is difficult. Okay, that it is very difficult to get the relation valid over the entire composition. As I showed by diagram, that maybe up to certain percentage of the solute, say 15%, 20%, 40%, not the 100%. So let us start here. Let us begin with this. Okay, so I am removing this top line. This is this I am writing. Gradually I will remove. It is better I start here. So what is the topic? Next topic. Next topic. Yes, we have few minutes left. So let us start the next one, which is the modification of the regular solution. Modified form of modified form of the regular solution of the regular solution the regular solution when the when the quadratic quadratic gamma I versus 1 minus xi relation is not valid. Relation is, I called you actually. 50. Okay, you just come in 2-3 minutes. Huh? Just be here. Huh? Is not valid. Is what happens? Is not valid. Underline not. Is not valid. Is not valid over the over the uh, over the entire composition range. Entire composition over the entire composition of range is of AB solution. Of AB solution of AB solution. A is solvent. A is solvent. B is solute. A is solvent. B is solute. That's right here. Valid. What is the validity range? Valid from XB is 0 to XB is, well, over, you stay there, stay back here. Is XB is 0.15 up to 0.5. Of course, is 0.8 only, up to this point only, depending upon depending upon the system. This is the next topic. Okay, this is the next topic we will discuss. So I cannot start now. The time is running out. Okay, so this is a we'll discuss. This is a topic that modified form, and it is actually why it is so not why modified. It is not valid over the entire composition up to a limited composition like this, 0 to 0.15 to 0.5, depending upon up to 0.5, depending upon the system. Thank you very much with this. So for your patience and for your cooperation and for your interest. So today we will call it a day and see you next day. See you next day for the subsequent 2 lectures. Thank you. Bye.